Number 10, we have some data, and we're going to find the range, mean, variance, and standard deviation. So I'm going to copy it, Control C, and then paste it here in Excel with Control V. And all these definitions are covered in 2.4 here. The range is the maximum data entry minus the smallest, largest minus smallest. Deviation, you find the mean of the data value, which is you add up all the data values and divide by how many there are. And each data value, its deviation will be how far away it is from that mean, the data value minus the mean. And we use that value of deviation in our formulas then for variance and standard deviation. So these two things, variance and standard deviation, are trying to figure out, give us a number to tell us how spread out the data is from the mean. And so to find the range, you need to take the maximum data value minus the smallest. And so you can use this formula to find the max. Make sure you get it right. The min, open parentheses. So 23 is the max and 12 is the min. So the range is going to be 23 minus 12. So our range is 11. Now the mean of the data equals average, open parentheses. Select the data, close parentheses. And that is the mean of our data. The variance of our data equals variance. And here we have a sample. It's a random sample of shoppers. So we want variance.s for sample. Open parentheses, select the data, close parentheses. You get your variance. And then our standard deviation equals standard deviation dot s, because we have a sample. Open parentheses, close parentheses, and you have your standard deviation. Now you may notice from the formulas of these, the standard deviation is always the square root of the variance. And we can just prove that right here. Square root, SQRT, of our variance is equal exactly to our standard deviation. And make sure you pay attention to how many decimal points you're supposed to be using for each of your answers. 10th would be 1 decimal point, 100th would be 2. Number 11 is trying to get you to visualize what standard deviation is showing us and telling us. So here we have data sets. Which data set has the greatest sample standard deviation? So standard deviation is a measurement of how far away data values are from the mean. And so if we look at this data set here, it's got some low values and some high values, so the mean's going to be in the middle, but all the data values are far away from the middle. They're either bigger or smaller. And so it has the largest standard deviation because the data is more spread out from that mean of 7. You can see how it's perfectly balanced around 7. So it has a mean of 7, but it has a large standard deviation because the data isn't close to 7. Which data set has the least sample standard deviation? That would be this one. It again is going to have a mean of 7 because 7's right in the middle of the data and it's symmetric. It's even on both sides of 7. But all the data is clustered really close to 7, close to the mean. So it would have a smaller standard deviation than the other two charts here. Now this graph here, it also has a mean of 7. 7's in the middle and it's symmetric on both sides. But its standard deviation is going to be in between the other two because there's some data values really close to 7, but then there's some that are bigger and some smaller. It's just kind of evenly balanced and spread out. And so that talks about how the data sets are the same and how do they differ. They all have the same mean, but they have different standard deviations. For number 12, we'll be using the empirical rule. And we can do that because we are assuming the data has a bell-shaped distribution. And so in 2.4, it talks about the empirical rule, which we need our distribution to be bell-shaped, which means it looks kind of like this. It's got a high peak in the middle because most of the data is in the middle, and then it's symmetric. It trails off evenly. The further away we get from the mean here in the middle, there's less and less data above the mean. And the mean in the middle, the further away we get below, there's less and less data below the mean as well. The empirical rule tells us that from that mean that's right in the middle of our bell-shaped distribution, if you're within 1 standard deviation, there's 68% of the data. If you're within 2, which means either 2 standard deviations above or 2 below, there's 95% of the data. And within 3, there's 99.7% of the data. either 3 standard deviations above or below. So for this particular example, it says the mean is 71 and the standard deviation is 5. So let's take that over to Excel. Our mean is 71 and our standard deviation was 5. So if you add 5 to 71, you get 1 standard deviation above the mean. Subtract 5, and we would get 66, which is 1 standard deviation below the mean. The empirical rule tells us 68% of the data falls between 66 and 76. If you do 2 standard deviations, we add 5 again, we'd get 81, subtract 5 again, 61. Empirical rule says 95% of the data falls between 61 and 81. And subtract 5 again, we'd get 55, and that would be 86 then for 3 standard deviations. I'm sorry, that's 56. 56 and 86. So an empirical rule says 99.7% of data is in between 3 standard deviations, in between 56 and 86. So just from knowing the mean and the standard deviation, you can find out a lot about the data if it's bell-shaped. And what in this case, between these two values they told us, those were the marks for 3 standard deviations above and below, 56 and 86. And so from the empirical rule, we know that 99.7% of the data lies between those values, or in terms of the problem, 99.7% of vehicles travel between those speeds. Number 13, we're going to be using Chebyshev's theorem. We need to know the number in the sample, and we need to know the mean and the standard deviation. And I'll talk through using the theorem, but the point of it is it's very similar to the empirical rule, where we're trying to find out how much of the data lies between certain values, but the empirical rule only can be used if we have symmetric bell-shaped distributions. And a lot of times when you're gathering samples, gathering data, you do not know what the shape of the distribution is, but we can use this theorem for any distribution no matter what. And so let's go ahead and use it here for our problem. We do not know the distribution, but we're trying to find out how many of the households have between 2 and 6 televisions, and the mean was 4. So we need to figure out how many standard deviations away from 4 these n values are. Notice how 4 is right in the middle of these two n values. Now our standard deviation is 1, so 6 would be 2 standard deviations above 4, because you would add 1 2 times to get to 6, and 2 is 2 standard deviations below 4. So essentially what this problem is asking is what percentage of households would fall within 2 standard deviations of our mean. And we don't know that it's a bell-shaped distribution. We can't use the empirical rule. We'll have to use Chebyshev's. And so the formula tells us we're going to take the number 1 and subtract 1 over the number of standard deviations we're looking for squared. And so to use that theorem, we're using the number 1 minus 1 divided by the number of standard deviations away from the mean, which we said was 2, that value squared. And so 2 squared is going to be 4. This is going to be 1 minus 1 over 4. 1 minus a fourth, which comes out to 3/4. So our answer is 3/4 of the data lies between 2 and 6. At least that amount. And so, well, how much data did we have? We had 36 values in our sample. What is 3/4 of 36? 75% of 36. So if you take 36 and multiply it by 3/4 or by 75%, you get the number 27. So from Chebyshev's theorem, we know that within 2 standard deviations, there is 75% of the data, which out of 36 pieces of data would be 27 data values are within that range. Number 14, we have a histogram, and from that we're going to try to make a frequency distribution and then estimate the sample mean and sample standard deviation. And so we have the midpoints of each of our different classes here in the frequency distribution, and we're going to have to use those to do our sample mean because we don't know the actual data values. So we use the midpoint of each class. So our first class is a midpoint of 70.5. And there was just one data value in there, so the number of data values multiplied by the midpoint gives you what we're calling x times f. X is the midpoint and f is the frequency. And so your next midpoint is 982.5. There's 12 data values in that class. And so we're going to take 12 times the midpoint to get our next value here. And then sum up all the frequencies, sum up all those multiplications, and then we're going to use those to find the mean of our data set. We take that sum of those multiplications and divide by the sum of the frequencies. And so in this example, 5725 divided by 50 gives us the mean for our data set. And now we're going to work out the sample standard deviation by hand. We want to take our midpoint here for each of our different classes and see how far away it is from the mean. So take each of these different midpoints. First one's 70.5, and you subtract the mean from that. So 70.5 minus 114.5, and you get your result. 92.5 minus 114.5, and you get your result. For each of them, subtract the mean. And then you want to take those values, and we're going to square them. So all the negatives end up being positive. Everything's positive when you square it. And so square all those values. And now we want to take each of those squared values and multiply it by the frequency, because some of these classes had a lot more data in them than the others, so we need to multiply by how frequent the data was in each of these classes. So that's this F that's showing up here. There was just one data value in this first class, so you multiply it by 1, it doesn't change. But the second class had 12 data values, so multiply that by 12. And so on. Do that for all of them. And then that symbol here means add it all up. So add up all those data values, and you get that. And the final thing we want to do is find the sample standard deviation. That's what we've been working towards. And so for a sample standard deviation, we always divide by 1 less than the number in our sample. And so we're taking this value, we're going to divide by 49 because there was a total of 50 data values. So I'll jump over to Excel. You would take that data value, which I have right there, and divide it by 1 less than our sample size, 49. And that is going to actually be the sample variance. To get to the standard deviation, then you take the square root of that answer. I just clicked on it, get that exact value without rounding. So the square root of that answer is then our sample standard deviation. And make sure that for your solution, you round to the correct number of decimal places. 15 is about the coefficient of variation, which is a great way to compare data with different units and how spread out that data is. And so what we need to do to calculate it, here's the formula, is find the standard deviation of the data and divide it by the mean. And then we're going to convert that to a percentage. And here's our data. I'm going to copy both or all of it, Control C, and we're going to paste it in Excel. And if you want to look at this in the book, we're still in 2.4. It talks about the coefficient of variation. And so for our 2 columns of data here, we need to find the mean and the standard deviation. So with the height first, let's find the average of the heights. And then equals standard deviation dot S, because we have a sample, open parentheses, select the data. And we have the mean and the standard deviation for the heights, so we can find the coefficient of variation. We take the standard deviation and we divide by the height, divide by the mean for the height. And this gives us the coefficient of determination for height. And then with weight, we want to do the same thing, equals average of all the weights, equals standard deviation dot S of all the weights. And we again want to take the standard deviation and divide by the mean for the weights. And to convert those to percentages, you want to slide the decimal point 2 spots over to the right, so 6.6% and 8.1%. And those are our 2 coefficients of variation. The one is larger than the other, which means that weight, that data has more variation than the other.